In this video, we'll discuss the beginnings of ancient Greek mathematics. Now, when we think about this time period, we're talking about the Hellenic Age from 800 to 336 BCE. At that time, there were two primary city-states that we often recognize, which was Sparta and Athens. Now, much of the work that we think of in science and mathematics comes from Athens because it was a democratic society that allowed all members to do intellectual discovery. Whereas the Spartans at that time were much more militaristic and minimalist, and so we know of less discoveries coming from the Spartans. Now, within Greece, there was often an agora at most of the cities, and this was across all of Greece. These agoras allowed for people to meet, not only do their trading, but also to share their discoveries and their ideas, and it was open to all citizens. And so from that, we get much of the deductive reasoning and proof and movements in discovery that occurred in Greece is because of the agora. So some of those key achievements that we think of come both from the philosophers through deductive reasoning, medicine, and even logic, to also major literary works such as Homer's Odyssey, which is from the same time period. Now, as the situation in the Hellenic Age continues, we see that Alexander the Great reunites all of Greece around 336, and they then move into their next age. So let's talk about some of the key people of this time period, one of them being Thales. He was considered one of the earliest Greek philosophers known by name and was known to travel the world, and that's where we think much of his knowledge would have come, all the way to what would consider the ancient Orient, to Egypt, and through Greece, and that's where a lot of his work and logic starts to show up. He's credited with some of the most initial logical reasoning and rational explanations that we have on record. Because at that time, when you think about natural disasters and what we call acts of God, the people believed that it was literally their gods that were causing things like earthquakes and volcanoes. Thales started to reason that there has to be some scientific reason for what's going on. His at the time was that Earth floats on water and earthquakes are just major waves causing the Earth to shake. So he's at least trying to think through that there's got to be something going on with Earth beyond just the gods are angry at us today. Now, also, Thales did a lot with geometry, and he would use deductive reasoning to help make some of our foundational geometric explanations. This helped produce different properties that we now use in geometry, and he also used it with the idea of similar triangles to determine heights of pyramids, hence how we know that he was traveling the known world at that time. Now, there are 5 foundational geometric concepts that we credit to Thales. These are that a circle is bisected by any diameter, the base angles of an isosceles triangle are equal, vertical angles formed by 2 intersecting lines are equal, 2 triangles are congruent if they have 2 angles in one side respectively that are equal, so it's the angle side angle congruence, and then an angle inscribed a semicircle is a right angle. These 5 foundational concepts we think of as going back to Thales. Now, let's look at that idea of the congruent triangles and the angle side angle, and where would have been the place that Thales would have used it. So one of the things Thales is known to do is be able to gauge how far a ship is out to sea from the edge of land. So how would he have done that? So we would start by drawing a line from Thales to the ship. Then he would create a perpendicular line that would go to point A. And that would be some known distance because that's on land from Thales. Now he would create a midpoint between where he is and where that known point is on land. Then he could draw a perpendicular line through A to go back onto land. And then once he's on land, there can find a point on that perpendicular line that would be a straight line through point B all the way to S. And if we look at what that creates, we end up having vertical angles, another part of one of his foundational concepts that then creates the angle side angle or congruent triangles, which means that CA has to be the same as ST. So by knowing a distance on land, he can know how far they are at sea. And that's one of the ways that we think he may have done it. There are other methods. Now, another famous mathematician of this time is Pythagoras, and he possibly studied under Thales He created his own Pythagorean school in Crotona, where they would study the quadrivium, which is arithmetic, music, astronomy, and geometry. He believed at the time that the universe could be understood through mathematics, and was pretty focused on the idea of not just that numbers were holy, but that whole numbers were holy. And that's kind of an important thing when we look at some of the things, the teachings of Pythagoreans. We know specifically that his teachings were oral, and that whenever something was discovered by the Pythagoreans, they went back and gave the name of it to Pythagoras. So there are some concepts we don't know if they came directly from Pythagoras or just one of his Pythagoreans. But they did make many different discoveries in mathematics, music, astronomy, and medicine. Now, from this group came the Pythagorean Brotherhood, which was pretty much a form of religion. In this brotherhood, they had farms. It was kind of like a boot camp, and it really did have a significant religious component. They had very strict rules to how they would do things, such as that a woman couldn't be married if she wore gold jewelry, or you can't pass a donkey line on the road. Where these came from, I don't know, but they're kind of some of the rules that we know. When you would join the Brotherhood, you would have a 5-year probation where you could not see Pythagoras other than through a veil. They were vegetarians, and for a long time, until the 19th century in the Common Era, that was called the Pythagorean diet. We now call it vegetarian. Women were allowed to be part of the Brotherhood, but they also had to learn other domestic skills. And the number 10 was considered one of their most divine numbers. And then whole numbers constitute the true nature of items. And that does lead to some issues because they have issues with irrational numbers. Now let's look at some of the accomplishments that they have. One of those being that they could calculate perfect numbers, which is the number in which the sum is the divisor. So we know this is true that if 2 raised to the n minus 1 is a prime number, then 2 raised to the n minus 1 times the quantity 2n minus 1 will be a perfect number. So let's give an example. 6 is a perfect number. What's its divisors? 1, 2, and 3. 1 plus 2 plus 3 is 6. So here is an example of a perfect number. Not only could they do perfect numbers, but they could also do amicable numbers. This is where two numbers, when you take their sums of their divisors, they'll add up to the other number. So think about 220 and 284. These were the two that they found to be amicable. Here, when I take 220 and add up all of its divisors starting at 1, it adds up to 284. Then if I take the divisors of 284 and add them up starting at 1, that adds up to 220. Hence why 220 and 284 are amicable. And there wasn't another pair found for over 1,500 years. Now, one of the ones that we know the most common is the Pythagorean theorem. Now, as we've said before, the Babylonians knew about the Pythagorean theorem, and we know other civilizations worked with the Pythagorean theorem prior to the Greeks. But why Pythagoras gets credit for it is that they were able to prove why it is the Pythagorean theorem. So let's start with the idea of a square, and we're going to split it into two measurements, a and b. And we can see that here we have the two squares, a squared and b squared, and we see those two white rectangles are going to be a times b. So this is a squared plus b squared plus 2ab. Now, what if we took that and we said, let's focus instead on those two rectangles. If I take the rectangles and split them into congruent right triangles and slide them to the corners, what I have there are four 1/2 a times b triangles, and then I have the hypotenuse of each triangle making up the square, and we can call that c. So the way this square is made up is we have c squared plus 4 times a times b over 2. Now these squares, the large squares, are identical, so we can take their two expressions and set them equal to one another. So here, a squared plus b squared plus 2ab equals c squared plus 2ab, because that's our simplification of 4 times ab over 2. Well, if I subtract 2ab from both sides, look what I'm left with. A squared plus b squared equals c squared. which is the Pythagorean theorem as we know it. Now, this may not have been how Pythagoras would have solved this, and there's been well over 40 different ways the Pythagorean theorem has since been proved, including by some of our presidents. But this is one way that we can visually see one of the reasons why Pythagorean theorem is true. Now, with that, we can calculate Pythagorean triples, which is where we have three natural numbers such that a squared plus b squared equals c squared. And we got two methods we use, the Babylonian method and then the Pythagorean method. Within the Babylonian method, we need two distinct natural numbers. And here, if we double those two numbers together, that will give us one of the values. Then if we take their squares and subtract them, that'll give us a second value. And then the values squared and summed will give us the third value. If the other method is called the Pythagorean method. And here we have two different ways depending on whether we have one number that's odd or one number that's even. If the value is odd, we would do m squared. Then we do m squared minus 1 over 2. That will give us the other one. And then they will equal m squared plus 1 over 2. If it is even, we don't need to have that divisible by 2. We're just going to double the very first term. So let's look at some examples of how this works. Say that we choose an m of 3 and an n of 2. If I'm going to use the Babylonian method, I double them together, and then I'm going to take the difference of their squares compared to the sum of their squares. And that gives me 12 squared plus 5 squared equals 13 squared. And the 5, 12, 13 is a Pythagorean triple. Another one, say that we decide to use the m, just the m, that's an odd number, so we're going to use the Pythagorean odd method, which is right here. So I'm going to take 3 squared, and then I'm going to say that's 3 squared minus 1 over 2, and then 3 squared plus 1 over 2. And when I do that, I end up with 3 squared plus 4 squared equals 5 squared, the 3, 4, 5 Pythagorean triple, one of the most common ones that we know. Now, the Pythagoreans really focused on rational numbers, and that's at that time what most people knew and what most people expected. They considered them to be divine. When we think about a rational number, that's p over q, which are both integers. Q can't be 0, and often we put the rational number in its irreducible form. Now, Pythagoras would not accept the concept of irrational numbers. When Hippasus came up with an idea of how to prove that square root of 2 was irrational, they drowned him for proving it. This led to some limitations in what we think about the Pythagorean theory of proportion, and the Pythagorean theory of similar figures ended up being invalidated because they would only focus on rational numbers. However, Eudoxus redefined how we think of proportionality, and his redefinition of understanding with irrational numbers was then included into Euclid's Book 5. Now, how might we show that square root of 2 is an irrational number? Let's use an indirect proof, or proof by contradiction. So that would mean we're going to assume that square root of 2 is rational. And to be rational means that we should be able to write it as an irreducible fraction. And we're going to call that a over b. So they have to be integers. We're going to square both sides and then solve for a. So when I square it, I'm going to get 2 equals a squared over b squared. So then that's going to be 2b squared equals a squared. By writing it that way, a must be an even number. So we're going to replace a with its expression of 2k to represent that evenness. Now if I square that, I'm going to get 4k squared. So let's solve for b now. And when I do that, I'm going to end up with b squared equals 2k squared. Now that b squared is equal to a double, that means it must be even as well. And therein lies my problem. We've now said that a and b are both even. That means that they are a reducible fraction because I should be able to divide them both by 2. However, our assumption was starting with it being an irreducible fraction. We've created that contradiction. That's not possible based on what we are given. Because that's true, then the square root of 2 cannot equal a over b, thus it cannot be a rational number.